I'm going to talk about universal Fechnerian scaling theory and applications. Most of it will be theory, actually, and very little applications. This is the outgrowth of a long-term collaboration with Dzhafarov, so it is more than fitting to have him as a co-author, maybe first author perhaps also. But he hasn't seen this particular set of slides, so if there is anything, blame it on me. Okay, I will start with a little bit of background on Fechner, then give you some basic ideas about how our Fechnerian scaling approach developed into generalized Fechnerian scaling, then the development of the dissimilarity cumulation theory, which is a much more general approach where the Fechnerian scaling is just one particular version of it. There will be some notations and some other concepts to be introduced. And then I will come back to Fechnerian scaling and look at a rather special case of Fechnerian scaling where we actually collect or have collected data or analyzed data sets that were found in the literature. And then finally I will come to a most recent development, the so-called ultrametric Fechnerian scaling, and I will demonstrate this by an example. Okay. Well, Gustav Theodor Fechner from 1801 to 1887. Most of you, of course, are familiar with this, and there would be a lot of things to talk about him. He is usually seen as the founder of psychophysics, maybe even of the scientific method in psychology. If you're interested, I would like to point you to one relatively recent monograph by Michael Heidelberger that gives you quite a number of information on the person and his work. So, what is Fechner's law? When we have stimuli with intensities A and B above or at the threshold, let's call them A and B, and O be the threshold, then in our terminology, now this is not exactly how Fechner would have written it, the subjective dissimilarity between those two stimuli, what he also called the Unterschiedsempfindung or different sensation, according to his law, is just proportional to the logarithm of the ratio of the intensities of these stimuli. There has been a lot of controversy and misunderstandings about how Fechner actually derived this law. And we have a recent paper in the American Journal of Psychology, the Fechnerian idea, where we have shown that Fechner actually derived his law in two ways, and both are mathematically valid. One way, which has been ignored in modern accounts of Fechner theory, is found in chapter 17 of the second volume, which has not been translated into English as a matter of fact. And actually what he explicitly writes there is a reference to Cauchy's functional equation. And he derives the logarithm by applying the Cauchy functional equation. Maybe not in that much of a rigorous way people would do it today, but still quite explicit. I'm not talking about the second way of deriving this because this would go too far for this talk, but neither of these two derivations uses the notion of just noticeable difference. So neither is based on Weber's law, and in most modern or older textbooks this is not really presented in a correct way, so they should really be rewritten. We will argue that his law and the derivations of it do not actually constitute the essence of Fechner's approach. What we consider as the essence is really the idea of additive cumulation of sensitivity values. And let me just expand on that a little bit. So Fechner suggests to present this subjective difference between A and B as an integral over the function h of x, where h of x is the first derivative with respect to the second, or the first, no, the second variable here, but it doesn't really matter. So it's a measure of the local sensitivity in the vicinity of the stimulus level x. And if you put in k over x for h of x, then this integral becomes the logarithmic law that he proposed. I should also say I will gloss about. I will gloss across a number of subtleties and details in the general development of our theory, just in the interest of time. But if you have questions, of course, we can go into that later. So here's a picture from our 1999 paper in the Psychonomic Bulletin and Review, the first paper that started our work. You see here the intensity scale, and this is the y-axis of the discriminability of stimulus level x at locally at this point. And the idea then of this additive cumulation of sensitivities is simply to take the integral from a to b across this function of sensitivity. So we then started to generalize Fechner's ideas in different ways. In the first version that we developed, stimuli are presented actually as points in a multidimensional Euclidean space. Any point x and any direction of change u attached to it can be then associated with a Fechnerian metric function h of xu, a multidimensional analog of the function h. Fechnerian is just a generalization of the Riemannian space concept. In the multidimensional case, responses greater or less, or brighter or less bright or brighter, cannot be elicited because they require actually the existence of a semantically linearly ordered property such as saturation, brightness, or loudness. So we have to replace this by asking observers to judge pairs of stimuli as either being different or the same overall, without giving any specific property, or in a specified way, like brightness and loudness. Both is possible. Any two stimuli can then be connected by a continuously differentiable path, and the metric function can be integrated along this path, yielding what we call the psychometric length of the path. And then the distance between A and B, the subjective distance, is defined as the greatest lower boundary or bound for such a psychometric length, obtainable across all possible smooth paths connecting A to B. I will come back to this concept in a simpler case. So if we have a so-called discrete space, that means that for every stimulus or every point there is an alpha greater than 0, such that the dissimilarity from A to any other stimulus of the space does not fall below this alpha. So a more special case would be even a finite set of stimuli.
That's a threshold.
Yeah. So in a discrete space, when we have a stimulus A here and a stimulus B here, so we would look at a possible path going from A to B, and it would be the oriented distance from A to B would then be defined as the infimum of the cumulated dissimilarities over all possible chains going from A to B. Okay. At space, here and in other generalized versions of generalized Fechnerian scaling, the computation of these distances is a purely psychological theory that it does not make use of their physical properties. Thus, the distance between two stimuli is invariant with respect to all possible relabelings or bijective transformations of the stimulus set. So we call that psychophysics without physics, because only the label of the stimuli is being used in this approach. Of course, we don't have to do it, but it's possible to do it on that level. So from now on, I will limit the discussion to finite discrete spaces. However, the theory of universal Fechnerian scaling and its underlying dissimilarity cumulation theory, as developed in 2007 by both of us and by Etibar in more specialized cases, is much more general. So now let's come to a first empirical example of what this Fechnerian scaling of discrete object sets is like. These are actually data from our own lab, if I remember correctly. We presented two letters, and subjects had to tell us whether they considered these two letters as being the same or different. It doesn't matter, the details of the experiment don't really matter at this point. But as you can see here, we have a matrix of these probability different judgments, and one stimulus was presented first, the other was presented second. Or they could have been presented also in other way. I will come back to that point in a minute. Yeah. This is actually only one subject, but we also had several subjects. Yeah. But these are replications typically of 80, 90 per pair. So most of the time they spend quite a lot in our lab then. Well, what you see here is that to say different when the two stimuli were actually the same in the main diagonal, it's not equal to 0, and it's not even constant over the different stimulus values. And moreover, it is not as symmetric in the sense that, for example, when C was presented first and A second, probability of saying different is 0.975, and when A was presented first and C second, it was close to 1. And so on. There are many cases of asymmetry in this matrix. So if one wanted to maintain the probability distance hypothesis as it was formulated by Etibar in 2002, one would have to say the probability to say different is a monotonic function of some distance d. This is obviously not the case here, because the monotonic function of some distance d would require these this function, these probabilities, for example, to be symmetric, to be constant in the main diagonal, and also we haven't checked it here, but the triangle inequality is not satisfied in this data set, for example. So in other words, we don't find metric properties in our raw data. Okay. Yeah, this is an important aspect of the Fechnerian scaling that what we define the so-called observation areas. You see, whenever we present a pair of stimuli, we either have to present them chronologically one after the other, like in auditory experiments, or at different spatial positions, like for many visual experiments. And each stimulus is always defined in reference to a certain observation area. It's a stimulus that is either presented first or second, or left or right. But it does not exist, so to say, in our experimental situation without reference to this observation area. And okay, there would be much more to say about that, but maybe I'll leave that for later. If there are any questions, just you can interrupt me anytime, okay? Yes?
Well, I just was thinking about how many trials this subject had to do, and I'm wondering maybe if the asymmetry is possibly coming from fatigue eventually in the trials. It's like, you got like one or maybe 4 trials, it looks like, out of 400 at every one of these.
Yeah, I mean, these data are not collected at one and the same day, but over typically maybe 20 sessions or so. And they are also, I mean, this is a problem that you always have when you collect a lot of data. Don was mentioning that earlier. But we also try to take care of the possible effects. It's not only fatigue, there are also other possible influences. But it's a problem in general if you have to collect that many data. Nothing would prevent us actually to do Fechnerian scaling across subjects, so it would also be possible. But then we, of course, would not have individual information. Yes?
About metric properties in the data,
Yeah.
symmetry is a critical property, but when you have people climbing a hill, the time that it takes to climb the hill and the time, so there are still metric properties there, but there is something else.
Yeah.
So, the metric may be hidden.
Yeah, actually, what we will typically get from our method is an oriented distance. Yeah. So the symmetry is not really that important. You're right. But the point is, and I will come to that in a minute when we compare it to multidimensional scaling as it is being done nowadays and also earlier, that there is a big difference between our approach of dealing with symmetry or asymmetry rather and the other one. Yes, Ethan?
May I just add, because you did not emphasize enough that the most critical deviation from the probability distance hypothesis is non-constancy of the values on the main diagonal. And it's extremely crude, as you say, 0.1, the first one, the other one is 0.6, then 0.5, and so on. This cannot be a function of a constant, right? So whatever even if it is a quasi-distance, between x and x it is 0, and any function of 0 should give you a constant, that we have a violation here. So I just wanted to emphasize.
Any other questions? So the basic building block is this probability here. And then we define psychometric increments, probability to say x is different from y, minus the diagonal element. And we have 2 ways to define psychometric increments, either in this way or in this way, although actually we only need one of the 2 types to go through with our computations. Let's assume, just for illustration here, that we have stimuli, and they are all in the observation area 1, or in the first observation area, and these are all in the second observation area. So what we are computing actually is a distance between stimuli within one and the same observation area. So we compute the distance between stimulus A presented first and stimulus B presented first. So it's not something we would be able to refer here, because here we always look across the 2 observation areas. But our method will give us an ordered metric on the observation area specific, either 1 or 2. Okay. How do we compute this distance or metric Fechnerian distance in one observation area? Now here you see this, let's assume this is just a finite hypothetical set of stimuli, and we want to compute the distance from A to B. So the weights of these edges here are defined by the psychometric increment. So if we take, let's say, the psychometric increments of the first kind, these one, we would go from A via some values to B, and we would look at all possible paths of going from A to B. And another way an equivalent way of saying that is we would go from A to B and back from B to A also across all possible paths, and we look at the sum of these two paths that means which become a closed loop actually, that have the smallest sum. So the infimum, or in this case just the smallest of all possible values. So this is the definition of the Fechnerian metric, the distance from A to B as the infimum, just as I mentioned before. So when we do that for one observation area, and we do it for the second observation area using the other type of psychometric increments, of course then we would be in trouble if we got different values here, but it can actually be shown, and that's one of the theorems, that the sum of these two ordered metrics, Fechnerian metrics, is identical. So it doesn't matter whether we do it in the first or in the second observation area. And so we have a unique and definition of the distance between A and B. What do we need in order to be able to do this computation? What is the condition for doing that? And actually it turns out that there is just a single necessary and sufficient condition in order to compute a Fechnerian distance on any set of same different probabilities, which is called regular minimality. And we say that an n by n matrix, or a row or a column of an n by n matrix, complies with regular minimality if it has a unique minimum entry, which is also unique minimum entry in the column. So just to give you a simple example, if we take first row here, the minimum in this row is 0.1, but it is also the minimum in this column. Here we have 0.05 as the minimum in the row. It's also the minimum in the column. And here we have 0.4, and it's also the minimum in the column. Okay, I should mention one more term here that I haven't formally introduced, but we can say that for each, when we go back to this picture here, for each stimulus in the first observation area, let's take A for example, we look at all possible values, all possible stimuli on the observation area on the second, in the second observation area. There will be, when we have regular minimality, there will be one stimulus that has that is the smallest one, and this will be called the point of subjective equality of A with respect to the observation area 2, and it is of course symmetric looking at this from the other observation area. Okay, that's right now what I think what all we need. We do have actually developed a permutation test to compute the proportion of matrices with a given number of violations, because if you have collected these large data sets and then you have just maybe one or two violations of regular minimality, you would really not want to throw away all of your data. And of course there are also other ways to repair this matrix, but in order to be somewhat satisfied, we would also like to have an idea about what is the proportion of violations that one might expect under certain random conditions. That was published in 2011. Okay, now let's step back a little bit and let's consider the more general dissimilarity cumulation theory, which is behind the Fechnerian scaling. So the Fechnerian scaling is just one special case of this DC theory. It deals with the computation of distances from dissimilarities, and it is in fact applicable to arbitrary stimulus spaces, imposing a topology and a uniformity on the stimulus space. So we are still in the situation where we do not need anything else from the stimulus set than the labels. So we don't need a physical dimension to define the stimuli. And it has been described in detail in 2007 and also in 2 papers by Etibar that followed. We will restrict the discussion here to the case of finite stimulus sets, avoiding issues of conversion and limits, although some generalization is possible. Maybe I should just mention the basic approach here was to define a topology on just using the dissimilarity judgments, or dissimilarity values, I should say, and then defining convergence and a topological uniformity, and then get to the representation in a Fechnerian in a metric. Yes.
By finite stimulus set,
Yeah.
you mean that the actually stimuli used in an experiment is finite, or that the stimuli presented in an experiment are sampled from a discrete?
Yeah, actually, both is possible. I mean, in practice, you will always only look at a finite set of stimuli, of course. But you, in one case, you may, in principle, have an infinite set of stimuli from some continuity of the physical stimulus space, for example. But we do have also just the case of a finite set of well-defined, like in the letters, for example. Yeah. Mm-hmm. So let this script calligraphic S let be this set of stimuli. Then we denote chains by boldface capitals as a finite sequence of objects, and then the union over all possible chains with elements in S is denoted by script S. It contains the empty chain and one element chains conveniently identified with the element, so that X element of calligraphic S is also the chain consisting of X. Then we can concatenate 2 or more chains presented by concatenation simply of their symbols. So we can build chains like this, chain X concatenated with Y, or element X concatenated with chain Y concatenated with Z, and so on. And given a chain, a finite set of sequence of stimuli, and a binary real-valued function f, we will introduce the notation fx, standing for this finite sum of f applied to x1, x2, x2, x3, and so on, with the convention that the quantity is 0 if n is 1, or 0 if it's the empty chain. So we this way we define the function f as this cumulation of these dissimilarities. In the literature, you find dozens of definitions of dissimilarity function. We have settled on this one here. We call it a dissimilarity function if it has the following properties. Positivity, so that d is greater or equal, is greater than 0 for any distinct stimuli, and the function d is 0 whenever we have A and A as the value to be where the D is defined. Then two critical properties, the uniform continuity and a certain property called chain property, are necessary when we develop the general case of the dissimilarity cumulation theory, and especially, well, the first paper, the 2007 paper, shows how this is being used. And then Etibai also did this work on the so-called arc-connected spaces and smoothly arc-connected spaces, where these properties are also critical properties. But in the simple finite case that we are using here, they are trivially satisfied. So a dissimilarity function as defined here need not be symmetric and doesn't have to satisfy the triangle inequality, of course. If it does satisfy the triangle inequality, then we call it quasimetric. So if we have AB plus BC greater or equal AC, the triangle inequality, then we would talk about it as a quasimetric. We also introduced the term deviation function, but I don't think we need it in this context. It's just a more general definition. Okay, now how do we get this quasimetric from this dissimilarity function D on a finite set? Well, it's basically defined as the minimum across all possible chains from A to B, applying this function D in the way that we defined the F earlier. Oops, like here. So we will get all these summed up dissimilarities from A to B. And we look at the minimum across all possible chains. And that gives us the quasimetric G induced by D. And then it is easy to prove that it is actually a quasimetric if we define it in this way. And now let's go back to the Fechnerian scaling, which you now can see is just a special case of the dissimilarity cumulation theory, where we define the dissimilarity function to be the psychometric increments. And so this would be the probability to say different to AB minus the probability to say different to the pair AA. And due to regular minimality, these quantities are always positive when B is different from A. So that is, of course, necessary for the definition of the dissimilarity. Then one obtains the quasi-matrix G1AB and G2AB, just as before, called Fechnerian distances, induced by either the psychometric increments of the first or the second kind. And then we, by adding these two oriented metrics, we get the overall Fechnerian distance, which will then also be symmetric. But as we already mentioned here, it's not always necessary or required to even do the symmetrization.
I have a question
Yes.
about the addition of
Yeah.
psychological reality and doing the addition. I understand that maybe we could give a good idea of distance from A to B, and a good idea of distance from B to A, which is psychological. But the adding is something that's done by the experimenter. It's not that the subject
Yeah.
is going to say from A to B and B to A, now I add them together, or see it that way. So, can you
Yeah.
comment on that?
I think Etibar did prove that this follows from a certain number of relatively innocuous assumptions. Of course, we have to make additional assumptions to come up with the addition, but it can be shown that it is then the only way to get to a symmetric function.
But you're not claiming the psychological reality.
No, it's not. It's not the claim. That's exactly. Yeah. No, we don't. We can just stick with one of the two. Yeah. Right. Okay. Yeah. No, it's okay. Mm-hmm. Any other questions so far? Okay. Now let's take a look at how Fechnerian scaling and multidimensional scaling are related. One might consider our Fechnerian scaling as an alternative data analytic tool to non-metric multidimensional scaling, rather than seeking a nonlinear transformation of a given set of dissimilarities into a usually Euclidean metric. DC replaces the dissimilarity value for each ordered pair of points with the shortest length, or the cumulated dissimilarity for short, over a finite chain of points connecting the first element of the pair with the second one, resulting in a quasimetric induced by the dissimilarity function.
But that's not really where the difference lies, because it's what you do with the quasimetric. In which space do you embed it?
Yeah, well, what we get here is just a Fechnerian distance. And this Fechnerian distance has no a priori relation to
Granted,
it's just a metric, so yeah.
Granted, but still, in the case of multidimensional scaling,
Yes.
the next step for once you have an order on pairs, the next step is to embed that in a multidimensional space. And we don't know here what you're going to do with that. Is there a space in which we embed that into?
Yeah, let's.
Dimensional?
So in the next step, it can be. This is the way actually we handled it so far. We view it as a complementary to metric MDS. Metric because we have the metric properties already. And then we can use a metric MDS on the Fechnerian distances to get Euclidean space using metric MDS. So that has been quite successful. Actually, whenever we applied it so far to empirical data sets, what we find is that the fit of the metric MDS solution based on the Fechnerian distances was much better than the fit of the non-metric values computed directly from the raw data. So although one would expect the fit for the non-metric to be better if it's on the same data set compared to the metric MDS, what we find is that if we use the Fechnerian distances and feed them into the metric MDS, we will get a better representation than the non-metric version on the original data. And I mean, the reason basically is, as far as I know, but there may be other variants of these MDS algorithms, the MDS algorithms are not really using the main diagonal in the data, if they exist at all. And the asymmetries in the raw data are simply taken away by averaging the two cells. So that's not what we are doing here. So that's at least our hope, or our argument is that our Fechnerian distance captures information that is already lost at the first step in the classical MDS approach. Of course, one would need to make large-scale empirical studies on exactly how these solutions differ, and so we haven't actually done that so far.
How complex is it to get these things? You have to search over all the chains.
Yeah, actually there is an R program, a Fechnerian, an R package in the on Fechnerian scaling that you can get very easily, and we have tried it with up to 60 stimuli, and it was relatively time efficient. But of course, you have to go through quite a lot of, possibly through quite a lot of chains. And there are certainly better, if we wanted to use it for even larger sets, we would need to come up with some tricks which to limit the number of possible chains going from one stimulus to the other. But there are some ways, some obvious ways to do that, to get to even better algorithms. Yes. Yeah.
You know, there is an estimation of the optimal algorithm. It's polynomial time. So
Oh yeah.
But
Yeah, it's the
cube of the number. Yeah, so it's quite efficient actually.
actually it relies on, I don't remember the name of these authors. Falkers, there's Floyd Patterson or something like that. Yeah, it's a well-known algorithm, so it's doable. Yeah. Okay, thank you. Okay, now I come to the last part, which is the so-called ultrametric Fechnerian scaling, which is very recent, and some of the results, there are only a few results up so far, and we are still working on that direction. Actually, no, I have one example here of the application to a, I think, well-known set of correlations between certain subtests of the Kennedy Institute phonics tests. This is taken actually from the book by Borg and Gronen on MDS, and they show that if you apply these data set, or if you feed this data set into the non-metric scaling algorithms, you will get a degenerate solution, meaning all correlations greater than 0.78 are mapped into almost the same small distance, and all correlations less than 0.72 into almost the same large distance, with stress value practically equal to 0. But it's not an informative representation of what is going on here. And we tried this on using the Fechnerian distances, and here you see that we, using metric MDS, we do get quite a interpretable solution of these admittedly very small set of data.
Where is the ultrametric coming in?
That comes in a moment.
Okay.
Yeah, that's not on. I was a step ahead of my talk.
Because I can.
No, there is no ultrametric
I
here.
can interpret the first one because it's ultrametric data.
Oh.
You would expect that.
Well, okay.
in
Yeah.
MDS.
Well, okay. Yeah. So yeah, the idea here is, given that many empirical dissimilarities on sets of high-dimensional stimuli, or with they have an underlying collection of hierarchical features, and they are sometimes represented by rooted tree structures or additive tree structures. So it seems reasonable to look for an alternative to the cluster analysis that is based on the principles of Fechnerian scaling. And the basic idea here consists in replacing the dissimilarity cumulation procedure by dissimilarity maximization. So given a chain and a binary real-valued function f, we use this delta notation here to define the maximum element in this chain going from in a given chain, so I should say. Again, with the obvious conventions as stated here. And then dissimilarity function m on a finite set is called a quasi-ultrametric because it's not symmetric, of course, if it satisfies the ultrametric inequality in this way. But this does not presuppose a symmetry here. And this is just the maximum of AB and BC is greater or equal to AC. Another way of stating this ultrametric inequality is to say that when we have three elements with three possible distances, two of the distances are maximal and equal, and the other is not larger than the third. So that's very well-known characterization of the ultrametric. Now, given a dissimilarity D on a finite set, the quasi-ultrametric G induced by D is defined by taking the minimum over all possible chains, where each of the chains we only pick the maximum element. So we take the minimum of the maxima of the chain elements over all possible paths from A to B. And then one can show that this is actually a quasi-ultrametric. And then again, we can define a symmetrization procedure again, which in this case would be a sensible way to do it, to take the maximum of AB and BA, to define that as the symmetric ultrametric on the set, which we then call the overall Fechnerian ultrametric. Now, this is just the beginning, so we have to find out actually what we get from this maximization procedure. And here's a simple example taken from Etibar's paper from 2010, which is not concerned with the ultrametric Fechnerian case, but the general Fechnerian or classic Fechnerian scaling case. So here we have a dissimilarity between 4 points. It's just a toy example. These are the minimum chains between any two of these. When there is a point, that means the direct path would be the shortest. Going from A to D, the shortest would be going via B and C. You can check that on that matrix. And the oriented Fechnerian metric in the original sense would be like this. And if we do the symmetrization by adding these corresponding cells, we would come up with this Fechnerian metric, which can easily be implemented in a one-dimensional Euclidean space, actually. This is a 2D presentation, but here you see the representation that preserves the values of these symmetric distances induced by the dissimilarity function in this example. Now, I'm showing you this trivial example because now we want to apply the ultrametric Fechnerian scaling on the same set. And if you check this, these are already different chains that we get by looking at the maxima. We get a different oriented ultrametric here, and then by taking the maximum, this is what comes out. And for an ultrametric, of course, we want, we know that we are able to present these data in a rooted tree structure, where the leaves of the tree correspond to the elements here, and that's what you get in this case. So you see that in this case, all the stimuli have the same distance to each other. So it's a very different structure that we get from the ultrametric. Okay, but this is, again, it's a trivial example, and we need still.
But
yeah.
Using the standard methods.
The what?
Using the standard methods of multidimensional scaling, the usual way of doing it, and the usual way of doing ultrametric scaling, you can't get, under the usual way of doing it, not yours, you can't get two good fits that perfectly fit the data in low dimensions. If it fits the data in low dimensions in one, it has to fit the data in high dimensions in the other. And that's sort of a mathematical fact about Euclidean geometry in tree structures. So you're actually doing something that's rather novel here.
Yeah, I know.
Very novel result.
Actually, if we used our ultrametric Fechnerian distance and apply all these cluster algorithms that are available, they would have to come up with the same solution, which otherwise is never the case, right? Yeah.
Have you related this stuff to Tversky's types of?
No, it would be an obvious idea to do that, but we haven't done it. No. Mm-hmm. As I said, we started this just a year ago, and I didn't really have that much time to work on it. So, but there's a lot of things to do. And let me just finish with a number of remarks on this ultrametric case. One thing that's very interesting that Etibar showed in 2010 is that he showed that the procedure of computing quasimetric distances from dissimilarities can also be described in terms of a series of recursive corrections of the dissimilarity values for violations of the triangle inequality. So whenever there's a violation in the triangle inequality, you repair it, so to say. You redefine the distance so that it becomes consistent with that. And he has shown actually that it does not depend on the order of doing these corrections. And together with his son, he has also shown that it's possible even to do in an infinite case with transfinite induction. I think that was a sequel paper. So that shows us another way of getting to the Fechnerian distance, really. And it can be shown that just mirroring this approach, we can do that also for the ultrametric inequality. So repairing the violations of the ultrametric inequality in very much the same way as for the triangle, we would also yield the quasi-ultrametric distance. Okay, let's just summarize a bit. On a finite set, any dissimilarity function induces a quasimetric by this dissimilarity cumulation procedure. We have now suggested a complementary approach inducing a quasi-ultrametric by dissimilarity maximization. A systematic comparison between these two procedures is left for future investigations. I showed you only this one trivial example. It is a principled approach to computing an ultrametric from a dissimilarity function. So as I mentioned already, any hierarchical clustering algorithm applied to these Fechnerian distances should result in one and the same solution. Unlike these algorithms, however, symmetry is not forced on the dissimilarities from the very beginning, but only after computing the quasi-ultrametric if we want to have it symmetric. Actually, unlike the DC theory, its ultrametric counterpart does not generalize to arbitrary stimulus sets. For example, for R-connected spaces, the Fechnerian ultrametric is identically equal to 0. There is some speculation that we might use another type of approach in order to generalize also the ultrametric to infinite sets. I mentioned that to Louis in Potsdam, I think, using the idea of a p-adic completion of the rationals. But this is just up in the air whether it really makes sense or not. I'm just also working on that. Okay, of course one can consider procedures intermediate between cumulation and maximization by defining a dissimilarity function for any chain, the length of the chain by this procedure here, like a Minkowski type of combination. And then for k to infinity, this would result, of course, in the maximum, so in the ultrametric approach just outlined. For finite k, this procedure is generalizable to arbitrary dissimilarity spaces. This follows from the fact that this is equivalent to the use of the original cumulative theory procedure in which one first redefines d into the power, the kth power of d, which yields another dissimilarity function, obviously, and then redefines the locally symmetrical quasimetric g induced by the power of d into g to the kth root of g. Moreover, the overall Fechnerian ultrametric is not the same for the two kinds of psychometric increments when we define it in this way. This was one of the main properties of the Fechnerian scaling theory, that we would get or end up with the same metric, but here it's the equality of the two sums does not have an analog in this maximum here. This could be kind of repaired by redefining the psychometric increments, for example, in this way, subtracting not AA or BB, but the minimum of the two or some other symmetric function of that. But that has to be explored also a bit more. Okay, this is just a list of papers, not complete on these things. We have only 2 procedure papers on the ultrametric Fechnerian scaling case. This is an early paper where Etibar defined the probability distance hypothesis and the idea of these observation areas. Then these are the papers on the arc-connected spaces, smoothly connected spaces, and this is the paper on the triangle inequality. This is the earlier approach, which I didn't really go into because I didn't have time, the theory of psychophysics without physics in the general infinite case. This is a paper in 2006 in Psychometrica where we show how to compute these Fechnerian distances in a finite, in the case of the finite set of data. And the most recent paper is the Fechnerian idea in the American Journal of Psychology, where we show that Fechner's derivations of his law are actually mathematically without fault, taken with a grain of salt, perhaps. Unfortunately, this paper was more or less ignored, as I found out in a recent meeting of the Society for Psychophysics. Even the historians didn't have a look at this, so we try to publicize it a bit more. Okay, thank you very much. Did I take too much time? It's okay.
We have a minute or
Oh,
maybe more,
okay.
you know,
Well, if there are
for some
any
good
questions,
questions.
yes.
So,
Yeah.
Did Fechner ever consider things like similarity between a bear and an elephant are the kinds of things that MDS is often
No, he
used
was
for?
not that I know. I mean, I wouldn't claim that I know all of his writings, but he was always very much limited to these.
Yeah, I'm actually wondering about the use of Fechnerian to describe all of this, because I think that taking the dimensions of physics as the basis were essential. And you mentioned Cauchy equation. Cauchy equation only makes sense if you have a continuum of real numbers to derive the form of the Cauchy equation. So I would call something like graph embedding of dissimilarities. How about that?
Well, we thought about this. I mean, we were stuck with this name because this was a beginning, really, when we started this, and it went further away. And it is really the idea of, as we mentioned already, the cumulation of dissimilarities that is the main point. But I don't think it's a bad idea to give credit to good old Fechner to some degree.
Well, I think it gives the wrong idea.
Well, that's of course a way of representing things, then, which can make that correct. Yeah, I agree.
Well, you have done the same, Jean-Claude. And you also called, your own development Fechnerian psychophysics, and
We can discuss that. I can defend my case on very solid ground.
over lunch.
Over lunch.
Who's the referee for the fight?
I didn't start that, Duncan started.
That's right, yeah.
By the way, Duncan
got it
wrote the
wrong.
review of this paper.
Yeah.
Duncan got it wrong.
Of the Fechnerian idea, yeah. Okay. Okay.
Okay, thank you.
Thank you.